All right, so just about 5 minutes ago, I uploaded a couple handouts for class today. The first one is just a lecture example that we'll do, and the second one is a worksheet that we probably won't have time to do, but I'm probably going to ask you guys to do it on your own and as practice, not as an assignment. Usually I give a practice assignment on this material. So I might give you that to do outside of class and maybe a couple more problems just for practice, but not for a grade. Let's see, who is here? So there were a couple people with technical issues. So I'm going to ask you to raise your hand, not visually, but on your, hit the raise hand button. Jeff, I haven't told you what to raise your hand for yet. You just gave me a thumbs up, but raise your hand or give me a thumbs up if you ran out of time. If you didn't finish the test, you submitted it, but it wasn't complete. Okay. I'm writing down names. Keep your hands or your thumbs up. There was one other person that wrote to me, but I don't see that person here. So the people who are not here, it may be that they're still trying to submit. I'm going to pause the recording. Sorry, Caesar. Thank you. I can always count on you. I thought I hit record. Sorry. All right, now I'm recording. Thank you so much. All right. So the height of the second rectangle is the y coordinate of that second right endpoint, where x equals 1/2. The height of that rectangle, that's the second rectangle. The height is f of 1/2, the y coordinate on that curve. And then the third rectangle, the height is the y coordinate of the point on the curve where x equals 3/4. And so that's f of 3/4. And then the fourth rectangle, the height is the y coordinate of the point on the curve where x equals 1. So that would be f of 1. So each rectangle, I'm taking, the width is always 1/4, but the height depends on the y coordinate of that right endpoint of that subinterval. And notice those rectangles are a little too big, right? They're all above the curve. So the areas, we're going to add up those areas and they're going to be a little high. They're going to be a little too high. So what we're going to do is we're going to say the area under the graph of y equals x squared is approximately the sum of the four areas of those four rectangles, A1 plus A2 plus A3 plus A4. And we're going to call that area, that approximation, is going to be called R4. And R stands for right endpoints. 4 means I'm using 4 rectangles. So we're going to use that notation throughout. R sub 4 means the region where we're taking right endpoints of subintervals and we're taking only 4 rectangles. And when I compute those areas, it's going to be width times height. So R4 is going to be, each of those has a different height, but they all have the same width. So notice 1/4 means the width, and f of whatever the endpoint is means the height of that rectangle. So the first rectangle has width 1/4 and height f of 1/4. The second rectangle has width 1/4 and height f of 1/2, because that's the right endpoint of that subinterval. The third rectangle, width 1/4, height f of 3/4. And then the last rectangle is width 1/2 and height f of 1. So each rectangle has a different height, and it is at the y-coordinate of the point where the rectangle hits the graph. And so when I compute f of 1/4, I get 1/16. F of 1/2 is 1/4 because we're just squaring, right? It's a squaring function. So 1/4 squared is 1/16. 1/2 squared is 1/4. 3/4 squared is 9/16. And 1 squared is 1. So I'm just computing f of each of those numbers. Now, notice that I'm not using decimals. That would not be exact. So please don't use calculators when you do these problems. You're going to have to deal with fractions and add fractions together. It's a little annoying, but you get used to it. Don't put things into your calculator unless we're trying to get an estimation. So in this problem, I will estimate it, but I will not put these fractions into a calculator. We don't estimate until the very end of the problem. That's when we put things in our calculators. So we can be as close to the real answer as possible. All right, so now I'm just gonna multiply those things together, add them together. When I added together all those fractions, I got 5/32. I mean, sorry, 15/32. That, if I put it into a calculator, is approximately 0.46875. That's an approximation because I chopped it off at the 4th decimal place. It goes on forever. Well, yeah, it goes on forever, and I think it repeats, but I'm chopping it off. So that's the sum of the areas of those 4 rectangles that we drew. And we can tell by looking at the picture that that's too big. We've gone way over. There's a lot of extra space. That's called an overestimate. I know that my area under my graph can't be more than that, but I can tell by looking at it, it's definitely less than that. So, I'm gonna change slides, but I'm trying to tell if people are still writing. I can only see 2 faces. Nicholas, are you still copying things down? Can I change slides? How about
you can.
I can, thank you so much. All right, you guys. So what we just did, notice all my rectangles were too high, and that was because I chose the right endpoint of each subinterval, and the right endpoint was higher than the left endpoint. So let's try it with the left endpoints instead. So we'll do the same thing, but we're going to draw different rectangles. So we're going to still use 4 subintervals. So what I'm doing, I'm using the same subintervals, but instead of choosing the right endpoints to get the height of each rectangle, I'm going to use the left endpoint. And notice that when I do that, it looks like I only got 3 rectangles. And that's because my left endpoint on the first subinterval, the y-coordinate of the left endpoint is 0. So the height, there's a rectangle there. It's just, it has height 0. So that's okay. So here's my region, my rectangles. I'm shading in the areas that we're going to compute. And there is a fourth rectangle on the far left. It just has height 0. So there wasn't anything to shade in. So each rectangle still has width 1/4, and we call the width delta x. That's the change in x, right? So each rectangle, each subinterval has width 1/4, and there's 4 subintervals. And now we're taking the height at the left endpoint. We're choosing the left endpoint. So the first rectangle, the left endpoint is at 0, 0, right? And so the y-coordinate there is 0. So that just means my height is 0 for the first rectangle. The second rectangle has, we're using the left endpoint. So the height, you can kind of see it. We're choosing the y-coordinate of that point on the curve. The third rectangle, we're using the left endpoint, 1/2, and the height will be the y-coordinate of that point on the curve. So that's the height of the third rectangle. And then the fourth rectangle, the last rectangle, we're taking the left endpoint, and the height of that rectangle is that point on the curve where x equals 3/4. The height of that rectangle is f of 3/4. So there's 4 rectangles there. You just can't see the first one. So the height of the first rectangle, H1, is f of 0. The height of the second rectangle is f of 1/4. The height of the third rectangle is f of 1/2. And the fourth rectangle has height f of 3/4. So then each rectangle has area 1/4 times f of whatever that right endpoint was. So my area under my curve is going to be approximated by those 4 areas, A1 plus A2 plus A3 plus A4. These are different rectangles from what we did earlier. The rectangles are different. And so we're going to call this approximation L4. L for left endpoints and 4 for 4 rectangles, or 4 subintervals. L4 means we're using left endpoints for the height, and we're using 4 rectangles. And so L4 is going to be the sum of 1/4 times the first height is f of 0. The second one is 1/4 times the height f of 1/4. That's the area of the second rectangle. The area of the third rectangle is 1/4 times f of 1/2. And the area of the last one is 1/4 times f of 3/4. So width is always 1/4. Height depends on the number we're plugging in, which is always the left endpoint. And so when I plug those numbers in, so f of 0, we said was 0. So we get 1/4 times 0 for the first rectangle. For the second rectangle, f of 1/4 is 1/16. So we get height 1/16. The third rectangle, f of 1/2 is 1/4. Then the third rectangle, f of 3/4, or sorry, the fourth rectangle is f of 3/4. The height is f of 3/4, so that's 9/16. So the first rectangle has area 0 because 1/4 times 0 is 0. So we're really just adding up 3 fractions. So those 3 fractions, when I add them together, I get 7/32. It's like less than half of what we got before. And when I put it into a calculator, I get approximately 0.21875. And this is clearly too small because those rectangles are shorter. There's a lot of empty space. And so when we add up the areas of those rectangles, we know that's not enough. It's less than the actual area that we want. So that's an underestimate. When we did the right endpoints, in the previous example, we got an overestimate. Our rectangles were too big. So here's what we know so far. We know that the area that we're looking for, A, we're looking for the exact area, right? And so far we've got 2 approximations. We've got an overestimate and an underestimate. So L4 is the underestimate, R4 is the overestimate. So the number we're looking for is somewhere between 0.21875 and 0.46875. That's all we know, somewhere in between those two. That's quite a range. So what we're going to do is try to get a better approximation and see what happens. So we notice that depending on which endpoint we choose, we get different numbers, right? If we use the right endpoint of each subinterval, everything's too big because that's an increasing function. So the right endpoint is taller than the left endpoint. And there's always there's stuff outside that we don't want. If we use the left endpoint, then the rectangles are too short and there's a lot of empty space. But what if our rectangles were skinnier and we had more of them? Would there be less overage or less empty space? So we're going to try more rectangles, skinnier and more of them. So I'm going to change slides. I'm going to try 8 rectangles. That means I'm going to chop up the same interval from 0 to 1 into 8 subintervals. And then I'm going to use the right endpoints just to see. I'm just going to do right endpoints. I'm not going to do it again for left endpoints. We're just getting an idea of what happens. So I'm chopping up my interval from x equals 0 to x equals 1. I'm chopping it up into 8 equal width subintervals. And then because they're all the same width, they have to have width 1/8, right? 1 divided by 8 is 1/8. So here's the x coordinates: 1/8, 1/4, 3/8, 1/2, 5/8, 3/4, 7/8, and 1. Those are my right endpoints. So here's my graph. And now I'm going to draw these rectangles. So we're using right endpoints. So I'm going to start at x equals 1/8 and go up And that's my rectangle. Start at x equals 1/4 and go up. There's the second rectangle. At 3/8, I get another one. At x equals 1/2, I get another rectangle. And each of those rectangles, the height is the y-coordinate of the point on the curve, y-coordinate that goes with those x-coordinates. So I've got 8 rectangles. They're skinnier. They're still going too high, but there's less extra space. That extra space that's above the curve is actually less than what we got before, when we only used 4 rectangles and we were using right endpoints. We had much more, well, maybe not much more, but we definitely had more extra space than we do now. So this should be a better estimate. And so I'm going to compute it. So I have to have 8 areas I'm going to add up. So here's the region, here's the areas of these rectangles. And remember, the width of each rectangle is 1/8. So delta x is 1/8. And so my area, I'm going to call it R8 for right endpoints, 8 subintervals. R8 is going to be the first rectangle area is the width 1/8 times the height, which is 1/8 squared. That's the y-coordinate of that point on the curve, squared. The second rectangle, the area is going to be width 1/8 times 1/4 squared. I'm going to do that with all 8 of those rectangles. So width 1/8 times the y-coordinate squared. Width 1/8 y-coordinate squared. Okay, those are the right endpoints. The y-coordinates of the right endpoints determine the heights of all those rectangles. And there's 8 of them. Make sure I have 8. 1, 2, 3, 4, 5, 6, 7, 8. So I squared each of those fractions. Then I multiplied each one by 1/8. My least common denominator was 64 times 8. Wow, yeah. So I did this problem. I really did it by hand. Yeah, 64 times 8. But luckily I could cancel and didn't have to multiply 8 times 64. I actually simplified it. I got 51 over 128. That's the sum of those 8 areas, 51 over 128. And when I put that in my calculator, I got 0.39843 approximately. Which is less than what I got when I did 4 rectangles with right endpoints. So the very first time I did this, I got 0.46 something. Well, it looks like we're going to have to continue this on Monday, but let me finish this slide. We've only got 4 minutes left, so this goes a lot slower than I ever anticipate, but it happens every time. So this is still an overestimate. So this is what we know so far. We know that the area that we want is somewhere between that first or the second example we did. We did 4 endpoints with 4 intervals with 4 rectangles with left endpoints. And then we got 0.21875, and we knew that was an underestimate. So now we're using 8 rectangles with right endpoints, and we got 0.39843. So these two numbers are a little closer together. So the thing we're looking for is somewhere between these two approximations. So I'm going to do one more slide, and then I'm going to go give you a shorter homework assignment, I think. Oops. So let me make sure everyone's okay. I'm going to change slides. So sigma notation is just the abbreviation. It's shorthand for doing a finite sum where we don't have to write out all the terms. So some of you may have seen this before. So if I want to add up 8 things, and they all have some sort of pattern, like in this example, A1, A2, A3, A4, they each have a subscript that's an integer, a positive integer. And the positive integers go from 1 to 8. So they start at 1, they go to 8. So the notation we can use is called sigma notation. And we write capital sigma, and that stands for sum. And underneath it, we write I equals 1 to say this is where it's starting. The indexes are going to start at 1. And then on top of the sigma, I write the ending index. So here the indexes are ending at 8. So sigma with I equals 1 on the bottom with an 8 on top means the sum as I goes from 1 to 8. I stands for index, and index is the little subscript. And what are we adding together? We're adding A sub I. So A sub 1, A sub 2, A sub 3, up to A sub 8. So as I said, the subscript is called the index, and that's what I stands for. And so in this example, I is going from 1 to 8. And to expand it, so I'm sorry, let me back up. So in the last examples, what we were doing is we were adding up areas. So we were adding up a function value, f of x sub I, times delta x sub I. And so we were using the number 1/8, and we were squaring the number x sub I. So what I'm doing here is I'm pulling the 1/8 out because each of the terms in my sum has a 1/8. So the distributive property says I can pull it out. I could just pull the 1/8 out of each term. So I'm using the distributive property here. And just a really quick example of the distributive property. If I have a finite sum where I goes from 1 to 5, and I'm taking the number I and multiplying each one by 2, that's just 2 times 1 plus 2 times 2, 2 times 3, 2 times 4, 2 times 5. Add those together. That's what that says. But notice each term has a 2 in it, so I could just bring the 2 out and just add up 1, 2, 3, 4, and 5. That's just the distributive property. So I'm going to stop here. There's no, yeah, we can't go forward. So what I'm going to do is I'm going to give you guys a short assignment just on sigma notation. So you will just, and maybe areas, maybe I'll have you do one area, a couple of area problems, but not a big assignment. And yeah, I think I can do it online. I think I can find a Newton homework that you can do online on area. And then I'll give you another assignment on sigma notation that is not for a grade, for those people who've never seen sigma notation before. So look for 2 types of assignments for Monday, but it's not going to be a major assignment. Part of it will be for a grade, part of it won't be for a grade. I apologize for going over again. Now, it looks like 1 or 2 people walked in late. If you walked in late and you didn't finish your exam, please stay. Everyone else, you guys can take off. And the people that I listed earlier who said they needed to finish, I'm going to give you another 30 minutes. And then the rest of you are not getting extensions, but if you walked in late and you need an extension, please stay and I will talk to you privately. All right, I'm kicking the rest of you out. Just stay if you need to talk to me about an extension on the test. And I'm going to stop recording.